This video is an interactive exploration of the numbers we put into tensors. Experts call this the centroid. Pause the video, grab 8 to 10 cards, then see you back here.
Okay. So, I don't have this plugged in. Sorry, Professor, we have to go into real class now. So, this will only take a minute, and then we're going to get into doing this as math. But it's the afternoon. You've been good souls so far. So, I want to give you a reward for having been patient. So, take whatever cards you have. They could be, as you can see, I was writing this when I had Pokemon cards. And this is called the Stacks Shuffle game. And some of you may know the solutions, and that's fine. I want you to choose randomly from your pile 2 cards. Okay? 2 cards, make sure you know what they are. Okay? And then just shuffle them into your deck, wherever you put them. But just remember your 2 cards, okay? All right? So you've placed them randomly in your deck. You may look at your cards at any time in this game. And you can move the card from the top of any stack onto the top of any other stack you make. Okay? Do you understand the rule? It's a simple rule. Just take the card from the top, put it on another stack. All right? And your goal is to swap the order of your 2 chosen cards. And the score is the number of stacks it takes you to do it. Go. Not the number of moves, but the number of stacks that you end up using to swap the order of your 2 cards and no other order. Okay, has everybody got some score for themselves? Okay. So I know some of you know the lowest possible score. Did anybody get it in 2? If so, you're a liar. 1, of course, is impossible. Let's go to DocuCam. Somebody did it in 3? Anybody do it in 3?
Yeah, we did it in 3.
Most of you did it in 3? Anybody do it in 4? Okay. So the minimum number is 3. And what does this have to do with tensors, I'll get to in a second. But let's see what's going on here. Just to make this somewhat evident, these are pretty straightforward cards to notice out of the deck that I have these others are numbers so that we can keep track of it. And I will go ahead and put them in order so that we don't have to worry about whether I did any reversals here.
Can you scoot it up just a little bit?
Can I do what, sorry?
Can you stack just up a little bit in the document?
I was just sorting them. So I'm just putting them in order so that we'll know that I put them back in order, okay? So I'm going to take my 2 cards, I don't care where I'll put it, but here, and then this one, I don't know, here. Just trying to put it in here in some random order. Okay. So I don't even see the 2 cards I have, but I've got to reveal it. So I'm going to move it. There I see my wild card. I'm going to move that over. Now, I can keep doing this. And all I'm doing to my deck is what? With just 2 piles.
Reversing.
I'm reversing, right? And I claim that's actually what Peter was doing when he had a product. He was really just moving that card to that position. And this is where all the ops were coming from. If I have x1, x2, and I start playing my game of moving things in the pile, I first have to move x2. So let's say that I call that one y2. Then I move it again. And you can see that I've reversed the order. Okay? With 2 piles, I can do nothing but reverse the order, whichever direction I'm going, right? Well, the solution when you don't want to reverse the order is that you just impose by fiat, you say, well, anti-order it, right? You put the words up on to say, I now choose to read everything backwards. And there's some clever notation you can use to sort of hide the fact that you're reversing the order. And this is the first actual sin in tensors. This was done by Whitney when he defined the tensor product in 1939. He said, let's do that to hide the reversed order, missing the actual mistake that was in his definition. I'm going to try to convince you that there's other definitions of tensor products that are more robust than this, that the tensor product you were taught has a mistake baked into the definition. Now, you can't say a definition's wrong, but you can say it's wrong for uses. That's what I really mean. This has to be reversed, and the clever trick of putting it on this side is that if I have x1, x2 times v, then I move them over, and you can see that I start to give myself the illusion of having fixed the problem because now the order seems to be correct for having acted on the other side. I haven't actually removed the reversal. I've just put it in a different spot so I don't notice that I'm hiding the reversal. To really sort this, though, to swap the two positions, x1 and y, eventually, when I reach my next card, I'm going to need another pile, another stack. And now I can put, let's see, what I should have probably started a new stack. I'm going to start my algorithm over. Just because I was trying to illustrate the point of reversal, so now I don't want to reverse. I'm going to try to move this out of the way. Okay, my third stack, third stack, third stack. Now I move this over. I put wild where that was, move this back to the middle, then reverse my stack back. And now, what I've done is reverse the order of my two cards, leaving everybody else the same. But it required a minimum of 3 positions. Right? So I can't do the yoga that I just did with just adjoints. It's just impossible. All I can do is reverse them, and I fall into this Whitney trap. So what I need is a third position. And this, to me, is what sets tensors apart from linear algebra. So I will give myself a third position. And if we were to give these more clever names, we might call it some kind of a derivative of some product, f times g. We'd have f times d dx of g, and d dx of f times g. Okay? And so this is where the name derivation comes from. This was done, I know, by Jacobson some time ago to talk about derivations of various algebras. Perhaps people like Killing and maybe even Sophus Lee could have seen this, but certainly many people in that era had made this observation that you can forget about derivatives and just do the algebra of derivatives, and you get a long distance. Okay? What I'm going to do isn't necessarily different, except that I no longer care about these being the same space. They're not functions coming from the same place at all. These are going to apply to arbitrary distributive products, UVW, where that star just says take something from this side, and end up in that side. And by distributive, I don't mean anything clever. I just mean high school, or maybe pre-high school. What's that called? Middle school? I don't know. Wherever you learn this rule. Preschool. Infancy. Some preschools some of you went to. Okay? Just distribute in 2 positions. And to write a 2-sided distributive law, you need 3 positions. And with 3 positions, if I bother to treat them all, then I can have myself use those 3 positions. Now, this derivation doesn't do what I want. We'll see what we will do with derivations near the end. But that's the first thing, is to allocate that there's 3 positions. And now I'm going to go to this centroid that people have been talking about and write that these three piles. Okay, so the three piles are one in this position, two, or maybe we'll call that one 0 because it's on the outside, and that one will be 2. Okay. So there's three piles all together, and with three piles, I can swap any two orders. So the hint has been given throughout the week about how you could sort this and make the thing commutative, and now you see that it's just this game of cards, that you can shuffle any two things. These are not perhaps surprising games, but if you're familiar with Eckman-Hilton arguments and other things in sort of higher forms of associativity that happen in topology and other category theory, you know that small ideas build and they give you some power over time. And that's the nature of the kinds of tools that we need in the background, is these small little lemmas to stack up into a more powerful theory. Okay, what we want to do next is explore this idea here. And in particular, some of you asked some good questions over the office hour break here. So we got into a discussion about multi-way arrays. Okay. With multi-way arrays, you can fashion a tensor, but I was trying to make the statement in my first talk that that's not enough to tell me what you mean by a tensor. And my examples were based on some story problems with Netflix and so forth. Now I just want to get very concrete for a minute. I want to think about a 2x3 matrix. And I want to ask myself, is this thing a tensor? Do I have contractions and so forth? In what sense is a matrix a tensor? And if you just asked a linear algebra student to say, what is a matrix? They might tell you it's a linear map. If it's an A student, right? So they might have picked up on what you kept repeating every day in class, and that might be that they could fashion a function on vectors that you just multiply the vector like this, and now it behaves linearly. So that's a form of distributive, right? We can do something like this. Now this interpretation says to treat the function as going from R3 into R2, all right? And then you're told to teach data science linear algebra, and you get your first Python package, or maybe it's Sage. You discover that when you're typing a vector into a computer, it goes naturally as a row, not as a column, and so the software is set up for that. And so the thing that you're actually doing is you're interpreting it this way, and all of a sudden it's not the same function, it's a function from R2 to R3, which maybe wasn't what you wanted. And so now you got to go back and forth and put some transpose in or something else to fix it. And you start to realize that to tell somebody that a matrix is a linear transformation is a lie. Because it's not until you tell them how you want to use the matrix. The data itself can be repurposed for a lot of things. The final one is that I can repurpose it as a inner product, the grand matrix of an inner product on R2 cross R3 into R. Okay? And I can take U, or maybe I'll put the M in here so we remember that there's a matrix running around. And now I realize, well, now I have to pick a denomination. Am I a row person or a column person? Because somebody's got to be transposed. And so, what was Pete's choice? I think it was rows. So then this one would have to be transposed. And then you also get told about complex numbers and that sometimes you need to put a bar on it. And you start to realize that to say that the matrix is a tensor is not enough information. Okay? That's the simple point that we need to know about when we're passing this knowledge on. So for my book, tensors are a regime out here, which can include multi-way arrays with an interpretation map. The interpretation map might be to say, take the matrix and multiply it as a matrix vector. It might be to be a vector matrix, or it might be a grand matrix of a form, something like this, to interpret it. And in fact, once you play with this a little bit longer, and you try to say, well, what do I mean by an interpretation map? If I'm not taking on board that there has to be an array behind it, but rather that I take data and I turn it into it, you run into Christopher's examples. Here you had a group, G, which was class 2, nilpotent, and it had some accompanying data. It had something like some number of copies of Z for what he called the cocenter. right? Some number of copies of z, and the center itself had some number of z's as well. Some funny numbers there. And somehow a tensor comes out the other end, right? And so you take these commutator maps, they depend on g somehow, and they become functions like this that output into, this, okay? So somehow I have nilpotent class 2 groups here, but with, of course, some interpretation to say how it is that I'm seeing a tensor in that thing, okay? So you can see it, it's almost the same notation. Notice the things that we've made interpretations out of so far. Over here I just used f. We could have said, just to fix the notation the same way I've been using before, is I could have said that's my interpretation function, this Brockett style notation. This one could have been an m on that side. They don't have to be angle brackets. They could have been soft brackets for all I care. They could have been square brackets. They could have been infix notation. It doesn't matter as long as you're reporting that you have a product that amasses some data together and gives you new data. And so that's actually what's happening over here. The interpretation is just that I have the bracket as my product, and I put a sub g to remind myself it comes from this group versus some other group, right? So my point is to focus on these things, and what's the minimum you need to describe that data, okay? So I'll put that down now, after I play with this toy here.
James, in your definition of a tensor, do you want to be able to move between different interpretations?
You can do that, but then you should have a theory of morphisms between them, and we'll get to those next. But absolutely, we're not going to have one tensor to rule them all. We're going to have many tensors that play together. Now, mind you, there's nothing wrong with taking a multilinear array and defining the tensor interpretation that's good for you and getting everyone in the room to agree with you, and then you don't have to write it anymore. That's fine. But the first time you write it down, you need to tell people what you mean by it. Okay, so this one. I distribute on both sides, right? So let me have a couple choices. I could distribute this side over that. So that's going to be u v plus v prime, u prime, v plus v prime. Or I could distribute the other way around, and I would have u plus u prime star v, u plus u prime star v prime. Right? They're the same because I can distribute on any side. That's required. Keep going. That's what I get if I fulfill the distributive laws on this side. On the other side, I get this, okay? Now you would say, duh, that's always true. Because you're probably thinking that addition has to be associative and commutative. But I'm willing to take a bet that if you just follow the theory, it tells you what it wants, and then you write that down as your definitions, instead of saying, I insist, like Whitney did, that we swap the order in some secret compartment thing and lead to the consequences. Sometimes you want consequences, you should put them in. But if you don't need it as a consequence, you should wait till you see what the theory really needs. So for my book, I would make the following rule be the rule that I care about. Because that's what's required in order to make something distribute. And then you can say, well, I mean, clearly that happens when it's associative and commutative, right? So if your addition is associative and commutative, you get this law. What about the reverse? Any takers? If I'm going to found a theory on the distributive law. I should know what the distributive law requires. It requires two operations. We could call them whatever we want. We call the one that's being distributed over the plus, and the one that's doing the distributing the times. They could be anything. So let's be a little bit generous with what anything could mean. So we can do distributive computation. Okay. I can have distributive computation where what I am going to do as my addition is I have lists of tasks, list of data, list of tasks, whatever, and I have concatenation as my plus. I can just keep adding to my task list, right? Pick two lists and add them together. Now that's not generally thought of as any kind of neat any kind of commutative set of rules, right? Just concatenate lists. There's no reason that you can move that data around, okay? But if I want to do distributed computing, if you open up the literature, there's a series of assumptions made about this, whatever concatenation it is, in order that you may distribute. And there's a reason for it. Because if I'm going to say, run this task, like say I say print, my lists, well, if it's a list that's built out of many lists, it's going to end up repeating the task on the sublist, right? So the premise is that this should do print, so let's say I have list 1, and I've concatenated it to list 2, then the obvious intention is to do printing of list 1 followed by printing of list 2. Is that clear? But how many of you have ever gone to the printer and it's not printed yet because what's it saying on the screen?
Jammed.
You have printed. So, warming up, right? The first person there has to do more work than everyone else. It's not a symmetric relationship, right? And most distributed computing has this kind of overhead that the first dispatch causes a sequence of events to happen, to allocate enough threads or do whatever they need to do, move data around, and then the rest get to go through the pipeline faster. And so what's really happening here is it won't distribute if you count all the nuts and bolts. There is a bigger cost for one printer than the next one. And will be the cost of coming to this lecture is that you'll get wet afterwards. So, and this is not the only scenario that happens this way. But to fix this, so Ohm's law is another example, right? You have current that's coming through a circuit, and it divides, it distributes along the circuit, okay? This is the boringest circuit ever. But it doesn't distribute evenly. What's it do? It's proportional to the resistance. So you can't make this actually distribute the way you'd like, but you can fix it. You can put a constant in front of the first task, and a different constant in front of the second task. And you can define this as the addition of L1 plus L2. And some new symbol. This is not the direct sum, this is just new type of addition. And it turns out that obeys this law, and it is not associative nor commutative. So in distributed computing, what you need is to be able to distribute your work, but you don't need associative and commutative because it doesn't exist, but this works. So I want to put distributed computing into this category. And it satisfies that law and not your standard laws. So let's give this a name. This is called medial. Medial for something to do with the middle. I don't know. Things that were named without my opinion. Okay? So I have any class of medial algebras. Anything that has that rule, I can then make a cogent story of distribution about it. This invites many things to the party that people were already doing, maybe under different names. Let me give another example here. So, examples from lattices. Well, I'll just do one from set theory, okay? But this is a general property that behaves in many situations. What happens when I intersect A with B union C? Maybe we should draw a picture. I take B, I take C, there's their union, and then I intersect it with A, which will be this one here. There's my A. What do I keep? Well, I keep the part that A and B share, and I keep the part that A and C share. So it distributes. And that's a lattice property that you can explore. A semi-lattice will even do. There are plenty of examples that are poset type things that have this distributive type quality built into them. Do they have negatives? Is there a minus that you can do that effectively works like canceling things out? Not really. So that suggests that we also have to give up on minuses and zeros. Just have the medial law. Now, I'm not telling you don't work in this box. I'm telling you the box is bigger. All right? So if you misunderstood my point as saying that I want to take a divergent view to what other people are doing, that's not it. I want to build a bigger fence so we can talk to more people. So here's my proposal on how to fix this all up. I'm going to come back to this word pre in a minute. I want to talk about a tensor space, and I want to be able to talk about using random data as inputs, and then I want to clean up the random data a little bit, so I'll take the pre away at the end. Okay. So a tensor space will consist of some finite set. These will be my axes. The elements will be axes. So just whatever sets you want. They could be labels of movies. They could be demographics. They could be resistors, or I don't know, whatever thing your data is about. Okay. I need a function from the set A, my finite set of axes, into medial algebras. Okay? Now, if you don't want to deal with other people's stuff, if you want to stay in your box, make your box where you like it. So if you like modules, go to modules. No problem. If you like vector spaces, go to finite dimensional vector spaces. I don't care. There's no problem in restricting this to modules or restricting this to vector spaces. Nothing's wrong with looking at a more narrow case. I'm just trying to make a case that there is a natural boundary already. These medial algebras. Okay? So each individual axis is assigned something, a module, a vector space, or some other distributable type of algebra. And then I set aside a base. This is medial, or whatever subset of families you want, and that's what I'll call the base. T is also, at the moment, is your data. I'm not responsible for how you write that down. It could be that it's class 2 nilpotent groups. It could be that it's multi-way arrays. It could be that it's quantum entanglements. It could be anything that you want to study using multilinear algebra. So that's your data. And the last thing is an interpretation map. So the interpretation map, it's responsible for taking your data and the axes you've picked and turning them into something that distributes. So there's a component here for your data, a component here for the axes, and then it outputs things in the base. So to write that all out, remember this little fishhook tail that I have on here? That's my notation to remind myself that everything in this data distributes. It distributes in every single coordinate, okay? Except perhaps in the t, because t is just somebody's random data, which maybe doesn't even have an addition, right? Just some crazy data. What this means is that whenever I pick a t in big T and I evaluate it there, then what I'm getting back is a function that's multilinear from the axes into the base, from the frame into the base. So this one up here I call the frame. Other words you can use here, legs and, wow, I'm not going to go through the list again. So at this point, if you wanted to talk about Christopher's examples, you could say that Christopher's T was nilpotent groups of class 2 with the parameters A and B. Right? That was his T. He shoves that group in here, and it gives back the commutator. The axes are 1 and 2, because there was a left and right to the commutator. The base is the center. Each one of those axes actually assigns the very same, in this case, module, which was the cocenter. And then the product was to just take the commutator, which he showed us was well defined. Elena's tensors, this space here was some random variable. Evolved into a tensor by taking S times S, or S times S, or expectation times expectation minus whatever the definitions were. Each one of those is providing a prescription for how to evaluate this function. That interpretation was given, then you go evaluate it. Your standard dot product comes out this way. Take a volume or area, as we talked about on day 1. You have some conversions to convert your miles to kilometers to gallons of water, whatever it is you need. That's the tensor space. Does the conversions possible? The product was a very simple product. Each one of these are examples of illustrating this pattern. Each one of them can survey parts of this space. Sudoku, for my purposes, will remain out here until you convince me that doing some linear algebra on a Sudoku puzzle is worthwhile. I won't endow this with an interpretation. That gets to stay as a multi-way array. But to become a tensor, I add to that interpretation. That's the model I take. And now, to Nate's question, what do you do with it? You can study it just like that as a function. And the way we study functions is that we start transforming them from one to another. We call those things morphisms. We try to come up with names. You've seen morphisms, right? You've seen many examples of morphisms. So, well, if they're taking this interpretation model on board, then I would have some VA to delta. That'd be something I'm doing some interpretation on. Maybe it has some other thing I'm going to interpret with, and there's no reason for it to have the same data. In fact, it could even have different axes. I'm going to limit myself for the minute to the same axis to draw some pictures. Later on Friday, we'll talk about multi-axes. Okay. So I want to put some functions to glue them together, right? I want to think of this as one object and this as another object, and I want a function between them to make some notion of transformation from one to the other. And the most natural thing is what we've been seeing in various diagrams, which is to start putting functions between the axes, one for every a, and then put some other function here. Maybe I'll call it f0 just to say it's not one of the a's. Okay. And then just follow your nose, right? You say, I start with my data here, which is some list of vectors. I apply t to it. Right, that's this thing here, so VA is a function on A. I apply f0 to the outside. Okay. Or I could go around here, which means to apply to each individual A the FA. And ship that over via S. That notation. In business school, flowcharts can end at the same place and be totally random noise. In math school, if you have a flowchart and you end at the same place, you put an equal sign between it. Even if they're not equal, right? That's just called weak equivalence at that point, right? So you just say, well, it's equal up to whatever I'm choosing to ignore, right? That's what you do in category theory. Some higher category clears up what I mean by equal. Okay, so we just declare if you end the flowchart at the same place from two different paths, they are now equal. Okay. Turns out that's not the only way to do it. But to explain what this is, we need a small digression. So, art school for a minute. If you think this multi-way array thing, then you're inclined to draw some kind of box. We've seen people drawing boxes. I've watched a lot of people draw boxes, and so I've discovered that not everyone can draw a box, including myself on some days. So this is a 101 on how to draw a box to give you a chance to communicate to other people. Okay, this is the worst drawing class ever. If you're really drawing a box, you put 3 points in perspective and draw with little lines and whatever, and then you get to go to Italy and have a different kind of career. But since we're mathematicians, this is art school for mathematicians. Step 1, hexagon. I like to hang my hexagon on the top. It doesn't have to be a nice regular hexagon. Whatever. Step 2, Y. Okay? Make your Y ugly if you need to. That's an outside looking box. So if you're trying to draw a tensor with a box kind of shape to it, and you just want to have like, this is the box, then it's a hexagon with a Y. What if you need to look inside the box? So you dualize it. 2 prime is an upside down Y. Now we're looking inside the box. There we go. We've now looked inside the box, right? Okay, now we want to put stuff in the box so we can start talking about how to move the data from one place to another. We've got to put things inside the box, so maybe there's some box inside this corner. We erase a little bit, and we draw a hexagon. And a Y. You got it. Okay, what if we've built ourselves this nice outside-looking tensor and we want to take a bite out of the corner? Draw a hexagon. And an upside down Y. Okay? It's not perfect. It'll get you going. Okay? Just hexagons and Ys and upside down Ys, you can draw pretty much any 3 tensor. What if you need a 4 tensor? 4 axes.
2 hexagons.
What'd you say?
2 hexagons.
2 hexagons. It's exactly right. Though you might put some dots in between. Okay? So I draw myself a big hexagon this time. Okay? And then I put some wee hexagons in. My Irish contingent appreciates the wee hexagons. And then I put some Ys in. Okay, the premise is that you need to have several axes. I know this is a bit of a toy. You don't have to draw 4. You can, at some point, you stop drawing pictures and you start just doing math. But there's actually something to learn from this picture. I mentioned that the reality is that machines do not store this grid of numbers. Okay? But physics even builds a bigger problem for you. If you start writing an algorithm where you have a 4 tensor, and you think that you can use any index identically, that's not true. Some of your data is spatially further than other data. It has to be. There's not more than 3 dimensions in your memory. In fact, in most memory, it'll even serialize it. So when you're just going from 1 to 2, I1, I2, I3, it might matter significantly which index you prefer. And it will slow your code down in major ways. This is where the people over in the other departments spend their lives, is trying to move your data to the indices that they can access quickly and not sort of this illusion we give ourselves that somehow all axes are created equal. They're not. They can't be co-located because of physics. Unless you're a string theorist, and then maybe you think that can happen. So, okay. I want to go back to this notion of morphism, and I want to ask myself, what do I do with a morphism when I have distributive laws? Well, distributive fits in the canon of algebra, so I should do algebra things to it. What does an algebraist do? I told you I would give you an opinionated take on what is algebra, and you haven't played with Legos yet, so that's where we're headed. So, Noether's resonance. So everybody, let's pretend there are sets. There aren't, but there you go. You take a set, right? Take a set X, and you might decide to apply an equivalence relation. Right? So you have the same data, but you're choosing to see some of it as equivalent, which wasn't necessarily naturally equal. What's another thing that's an equivalent way to say that? A partition. you have a partition, which is X mod the equivalence relation, right? You sort of think of, well, I just make a new set whose elements are the equivalence classes, right? Those are interchangeable concepts. And there's one other interchangeable concept, which I could have thought of as a function into some set P. And the application of this would mean that any two that are equal go to the same place, so the fibers are returning the partition. And if I had a function, I could induce an equivalence relation by saying, did they go to the same place? Right? And I could have started from anywhere. I could have started from a partition up here. I could have started from a function here. And what will happen is that once you do this, you go around, right? Once you start cycling between the three interpretations, you don't find a new one. You don't get a new, smaller partition. You get into a resonance. You get stuck inside there. That's true of any set. And what is algebra? Add operations. You add pluses and minuses and times and whatever. And then you insist that the equivalence relations respect them. So for example, if I had addition and I'm saying A is now congruent to B and A prime is congruent to B prime and I have a plus, then I want this to be true. That's called a congruence, right? Why am I saying this to you? Well, because I'm doing this for medial algebras where you don't know anything, where you don't have things like the kernel. What's the kernel of something that has no zero?
Equivalence relation.
It's the equivalence relation, right? A typical example, though, is the null space, right? We don't have a null space because these don't even have a zero anymore, right? And we're going to do it for this even more crazy space. I have to respect the operations. The partition has to have a well-defined multiplication. Or sorry, this times this, that this needs to be well-defined. That's the same as that statement. What's the word I would have to add to this kind of a function? Rhymes with homomorphism. Anybody?
Homomorphism.
Oh, there you go. Okay, so these things are all the same thing, right? They're all interchangeable, and that's what we teach all our students, and we take somehow an entire course or more to say the same thing, okay? You can either have a homomorphism, or you can have a congruence, or you can have a partition that's called a quotient. All right, we give them fancier names now. Okay.
Notice just the homomorphism is surjective here.
This one's surjective. Down here is any homomorphism. The way I'm writing my cycle is I take any homomorphism, and then I can induce a surjective one, which would induce the equivalence relation, the partition, and then here it becomes unique. But wait, there's more. Let's get the boring ones out of the way. The classic Eckman-Hilton argument is that if you have a medial algebra and you also have a zero, that implies that it's a commutative monoid. It's a commutative associative addition. You can follow that with Grothendieck to turn this into an abelian group. Well, you have to have some conditions. For example, the easiest solution is to just say with cancellation, or just you might lose some stuff. For example, if you're doing the lattice-related examples, don't do this, because they don't have cancellation. They will give you an abelian group that's pointless. So, but you can head to abelian groups and have subtraction, and then from here, boy, you just start to dress this up. You throw on centroids, why not? And then you're off into making modules, and the rest of the story of moving it inside that box, moving it inside that list of arrays kind of interpretation. So these are all fair, you know them. If you had them already as assumptions, fine. But what I'm trying to point out is that you don't need them as assumptions. They come for free. Medial plus zero got you a commutative monoid. Commutative monoid could have got you an abelian group. Centroid could have put scalars on for you. You didn't need to give any of that to your users, which means that when you're trying to find it in real life, it's easier to give the simplest definition, meaning it has the fewest moving parts. Let the algebra build the right scalars for you. Don't start out saying it must have these scalars, because you're probably wrong. It'll have whatever scalars God gave it. That's what's the phrase, non-denominational comment. An Einstein God or something. So, okay, so that's the easy one. Less easy.
Is centroid here somehow in the sense of this morphism picture?
The centroids are going to affect, the point is that if you have something that's a centroid and you have one of these morphisms, it'll turn all of these into semilinear maps for that centroid. The centroid is actually the largest set of scalars for which your product is distributive. So it's a universal mapping property on, and I'm not going to go into it because I think some people will say it, or we'll say something on Friday. I want to get to a particular point here and play with Legos. So, so there's another thing. What if you don't have zeros, but you have, so medial quasi-group. Whoa. Gosh, did I ever learn that? No, you didn't, and that's okay. So a quasi-group just means that these two equations have solutions and they're unique. There's no subtraction. I can't subtract A from B, but I can still solve it. Plenty of examples. I'm not going to talk about it, but the examples that we've given are like that because of this theorem. It turns out if you have a medial quasi-group, then the, let's see, who proved this? It would be Murdoch-Toyoda, and Bruck. Bruck is sort of a big name in universal algebra. He's also my great-grandfather mathematically. No, my grandfather mathematically. Okay. So these folks together and independently proved that then the medial, then the addition is a twisted abelian group. That's that scaling the C1 and C2 like the resistors, like Ohm's law, where it splits up and you just do it proportionally and you make an affine shift. What does this say? It says that having bet on medial wasn't a bad choice because it's actually hiding a group in the background. You're not that far from a group. It lets you take more real life in without losing the tools of algebra. And in particular, the consequence of this, which is not at all obvious, is that these are ideal determined varieties. What am I saying? Well, that's fancy speak for saying it does make sense to talk about the things that go to zero. So if you have a homomorphism and you create the congruence that you get from just saying I have the same fiber, that this is in fact determined by setting all the values equal to some distinguished symbol. So that there's a notion of a null space.
Davey and Davis also show that the set of distributive products U1 through UN on medial sums UA is itself a set with a medial sum. Corollary, every pretensor space maps uniquely into a space with a medial sum. This lets us define a tensor space as a pretensor space with a sum. We can now add tensors, even crazy ones.
And so that's the claim I want to play Legos with now.
James, are these in that sentence, are they medial plus zeros? Or
No, medial
what
quasi-groups. Medial quasi-groups
So these
are
then?
ideal determined.
Got it.
Medial quasi-groups, whatever they do to create identifications between things, they're secretly like a null space. Which means you can still do linear algebra. They can be talking about randomly really cool stuff like distributed computing, but they're doing linear algebra behind the scenes. There's work hiding in the twist, right? You've got to do the twist. It's a little dance. But no, don't do that one. But the net result is that you can get back to linear algebra. That was the whole goal, is to like not leave algebra out of the canon because that's where we get all the power of tensors is the linear algebra in the background. So this is saying you can do it. So when you extend the fence, you don't actually end up getting hurt. You stay on a plateau of nice soil. What do we get from this now is that this here also has Noetherian resonance. And fact, you can add to Noetherian resonance now with a stop at ideals. Now some of you feel like, well, come on, you can't have ideals. Groups, for example, don't have ideals. What's the definition of normal? If I have a normal subgroup of a group, what's that mean? Some of you know.
It's like closing a conjugation.
Yeah, it's closing our conjugation. So really the point is that groups are rings with a conjugation product, and this is less than n. It absorbs the product. So normal is just an ideal condition written stupidly. Groups are rings. This here is a big multiplication, and now we have opportunities to absorb in lots of places. Oh, sorry, I want to absorb things. I put all of V1 into that position, and then take, I2 up to IN. And ask for that to be inside of, say, delta 0, then this would be one way of saying that these other subspaces are absorbing the V1. I take subspaces IA of VA and delta 0 of delta, and I add the condition that it absorbs V1. Just like a product absorbs in a standard ring theory thing, like in a ring theory class, you would say that's the left absorbing property, right? But now I have more than two spots, or maybe I have more than two spots. So
At this point, the video recording ended and we played with Legos. What was the point? To try to build ideals from tensors. Think of the drawings as hexagons, or get your own building blocks, and see what you can build. Can you take your tensors apart with algebra? Here are some that we built. This one is known as a left ideal. We can take any values on the left, but when we encounter the ideal, it absorbs it into the background. The missing space proves that we've absorbed the values into the ideal. Here is its counterpart, the right ideal. Now the absorption is to take anything on the left, and it'll be absorbed into the background on the right. There is a missing gap, the absorption line. A two-sided ideal is both a left and a right ideal. But with tensors, we have the ability to discover brand new, never-before-seen things. like this three-sided ideal, which works outside of the usual algebra. In conclusion, tensors aren't just data tables. Sometimes you need to think of them as multiplication tables. So whether you're interested in data or the math, algebra can help. Hope you learned something new, or at least got to play. Until next time.